Good morning, Hui.
Morning.
I got a request from Joseph to record today's session, so I am recording. So we'll give other folks a couple of minutes to show up if they want to, and start screen sharing. So everyone did pretty well with shear and bending. Biggest problem seemed to be what I figured it would be, which was which direction, default direction, do we want for positive and negative, starting with the distributed loads, and then matching that up to the FBD. But with that exception, I was pretty impressed. It takes a lot of practice. It's tedious. So by the way, when I graded those, what I was mainly looking for were, first of all, did you get the support reactions right? And then second, did you have the right order of polynomial for each interval? Because that's something you can almost just call out looking. If you have a constant distributed load, you'll have a linear shear and you'll have a parabolic bending moment. If you have no distributed load, you'll have a constant shear and a linear bending moment, blah, blah, blah. So that's kind of a clue. So if you're going along creating your expressions and all of a sudden you're like, wait a minute, why do I have a term that's to the fourth or fifth? I only have a constant distributed load, maybe add an exponent wrong or something. So hardest part is the boundary conditions between intervals, wasn't it? At least that's what I think. Not seeing anybody yet. I'll tell you what, I have 3 different centroid and center of mass problems queued up. So I'm just going to get started and other folks can dive in as they join. Hui, have you taken a look at any of the centroid stuff yet? Or have you ever done centroid calculations? There's no? Oh, let me get chat over here where I can see it. Okay, cool. That'll help. Yay. And I'm going to turn my video off, save some bandwidth. Okay, so we'll start with the definition of centroid, basically, or center of mass, if we throw in density. So we can say a vector from some reference point, we'll call it O. So I think we're going to use this one for O on this problem, to the centroid is equal to 1 over, in this case, we're looking at 2D. So we're looking at area centroid. The whole area times the integral over that area of R So you get a little area dA here. We're going to draw a radius vector to that. And we're going to just keep drawing radius vectors to every one until we have added up the sum of the radius vector times the area, and we've got the whole area. If you've got like a line, say we got a wire or something here. We can draw a radius vector from the origin to some spot ds, and we could describe the centroid of this piece of wire in 3D, kind of the same way. In this case, the radius vector from our origin here to whatever the centroid on this crazy bendy wire that's out here in space, wire centroid, is going to be 1 over the length times the integral over the whole length of wire. And we'll just integrate from one end to the other. One radius vector to another radius vector, and we'll add all that up. And obviously volume, we do the same thing. You know, you got some big blob. I'm in love with Cartesian coordinates, which I shouldn't be, because so many things are round. Say we got a cone or something that's obviously 3D. And so we could define a little arc-shaped volume unit with a little height, dv, and we can draw a radius vector to that. And so in that case, the radius to the centroid is going to be equal to 1 over the whole volume. I'll say Vt for V total times the integral over the whole volume of the cone in this case, of R dV. So it's all the same. So it's a ratio of the average distance from some reference point integrated over the whole thing divided by the whole volume, the whole length, or the whole area. So that's the definition. And it's you might see it in terms of a balance point. So we'll use this 2D shape. Pretend that there's a gravitational field and that this shape has some weight to it, or has some mass, sorry. Has some mass, and we're going to put it in a gravitational field G, so now it has weight. You know, the X centroid would be the point around which it would balance. You know, so the sum of the forces on each side due to the weight of a uniform density object would balance. And this should start looking familiar at this point, because we actually defined centroid, in this case the X centroid, when we were looking at the moment due to a distributed load, because we're actually going to use that as, in fact, you kind of just saw it hopefully before I erased it, this term RdA for something where A can be expressed as the differential of some function, in this case of X. So we'll express Y in terms of X, and then we'll define like a strip that's the whole strip's at the same distance. But that's going to look an awful lot like describing the moment due to a little bit of a force distribution. So you've already seen the same concept of adding up the contributions of a strip or a bit of something at a distance from something else. And that's literally the definition of centroid. So we didn't mean to call it centroid back then, but it was the same exact concept. So hopefully it'll ring some bells. All right, so let's just look at this shape. It's we have some kind of power law function, y equals x raised to the 2/3, and we're looking at the function from the origin here to 8 inches. And if we want to find the centroid, We can define R from point O to the centroid in Cartesian coordinates. So we're going to have an X centroid in the I hat direction. So we're going to go over so far, and I don't know, I'm figuring it's going to be somewhere like here maybe. Actually, I'm being redundant. Centroid is either X sub C or X bar, and I think our book has X bar. So I'm going to use X bar. Sometimes C means center of mass, and we haven't included a density. So let's just keep it all about centroid. So that means we're assuming uniform density. With center of mass, we gotta worry about where is the mass geometrically. Now we just want to know where's the geometry geometrically. So a radius from the origin to the centroid is the distance in the x direction to the centroid, in the x direction, in the I hat direction, plus a scalar distance that represents the distance from O to the centroid in the j hat direction. So now I made myself a little vector. So if I just knew what that scalar value was and what that scalar value was, I could slap them in and I would have a radius vector that points from the origin to the centroid, which again, I'm going to assume is probably going to be somewhere around here, just eyeballing it. And what I'm eyeballing is for my x centroid, is this area about the same as that area? Maybe I don't have it quite in the right. And then for the y centroid, where's my eraser? And then for the y centroid, the area of the 2D dimension would say this y value is the y centroid if this area below it was about equal to this area above it. Actually, it would be exactly equal. My eyeballing it where I think it is about. So I'm thinking it's going to be somewhere in there. The reason I'm doing the eyeball swag is, again, a check of my math. If I make a math boo-boo integrating and I basically pick a centroid that's maybe off the shape or way up at the end, I know to go back and take a look and make sure I'm okay. So what's nice about integration is, say I'm gonna define this again. I'm gonna write it again. So the radius is going to be 1 over area, the integral over the area of r dA. This is the same as saying we can define any r as, oops, not that particular one, that's what we're solving for. Any y because that's r, right? So the integral of a sum is the sum of the integrals. Remember that. I know it's reaching way back into the past when you took calculus for the first time, but that concept of integrals gets repeated again and again with centroids, center of mass, and moment of inertia. That really simple fact makes life really, really easy. It's the foundation of the parallel axis formula for moment of inertia to a great extent, and then more directly, the method of composite parts and composite areas for figuring out center of mass, centroid, and moment of inertia for complex shapes. You can divide them up. So we can go over that a little bit later. And that's also front and center in the book. And in my notes, I go over the actual proof of it from integrals. But we can also apply it to our radius. So if I want a radius vector to the centroid, I can separately treat the x part and the y part. So I can integrate, I can take 1 over the total area. I'll do a total here, just to remind myself. I can integrate over the whole area. X dA. And then move in the a hat direction that distance. Divide by the total area, then I integrate over the total area of y dA, and I move that much in the j hat. Oh, and if this were 3D, we could just repeat that with z. So easy peasy. So now all we have are really to do are figure out these integrals and maybe calculate the total area. So let's see, let's start with the total area. The area, the shaded area is the area under the curve. So I can do some calculus and I can integrate from this point to 8 inches under this curve with respect to x. So I can do the integral of x to the 2/3 dx, and that'll be +1 plus 3/3. 2/3 plus 3/3 is 5/3. From 0 to 8 inches. I'm going to assume, I'm going to drop the units, which I really hate to do, because this function doesn't have a little constant in front of it to make sure the units kind of match up. Honestly, we should be getting a value in inches square. All right, thank you. I'm going to let you, my calculator's charging, so let you do that. Okay. And we're going to presume this is in inches squared. Okay, so let's go after, this is x bar, and that's y bar. So next, let's go after x bar. So we're going to figure out where I'm going to okay, thank you. Gets easier. So I'm going to do the strip method here, because to get x bar, I'm going to need to integrate with respect to x. Speaking of which, before I do that, I'm going to define a dA. We can do this any one of 2 or 3 ways. And I shouldn't be drawing my strip yet. I can either define it as a function of x dx, so that's width, differential width in the x and some height in the y. I can define it as some function of y dy. So the first one would be vertical strip width dx and a height equal to 0 and x to the 2/3. So x to the 2/3 minus 0. So our function of x would just be x to the 2/3 and dx, length times length equal area. And the next one, we'd have to define some kind of horizontal strip, because that whole strip would have to be the same distance y, because we're looking for the y centroid. So we're going to add up all the area that's the exact same distance in the y direction at one time, and that add up all those areas with their specific distances. That's what we're doing here. That's what this is literally telling us. So now the trick is, how do I actually do that for a given function? So, well, here's my y, which was easy enough. Get rid of that. But defining this area is kind of the trick. Well, I got my dy. I got my height, my differential height. But now I need, I basically need my length for my strip. So the length is going to be, it's 8 inches on one side, and it's, which x is this? Well, I want an expression in terms of y, because I'm going to integrate with respect to y. So, you know, what x goes with that y? Well, if you can write the function, you know, basically each variable in terms of each other, you can swap dependent and independent variables. I could raise both of these to the 3/2 power. Do a little basic algebra. I think. 2/3 times whatever equals 1. Yeah, 3/2. %99% of your errors are in basic algebra. always keep a calculus book and an algebra book nearby. That's why I have Paul's math notes bookmarked all the time, just in case I forget something super fundamental. So if I want to oh, this is so basic. Do to each side the same thing. So if I want to turn this into a 1, I have to do the same operation. So what do I have to do to this side to get an x to the 1? I have to raise this to a power, which is equivalent to multiplying the exponent by something. So, because I'm not going to multiply by an x to the 3/4, so I would have to raise it to the 3/2. So now I have a y as a function of x. So y to the 3/2, x to the 2/3, 2/3. And it actually isn't that, it's 8 inches minus that. So as y gets bigger and bigger and bigger, this distance should go to 0. And in fact, we can check. Our strip should have a 0 length at 8 inches. So what's 8 raised to the 3/2? It doesn't look right. Oh, it's y. Sorry, it's 4. Thanks. It's a function of, sorry, I have the wrong function. I'm not raising 8 to the 3/2. I'm raising 4. Thank you. Should be 4 to the 3/2. Oh, it's an algebra day. So that's more like it. That's 8. Check. Notice it's a function of y, not x. I'm looking down on the x-axis. I'm integrating with respect to y. So y at an x of 8 is 4. So 4 raised to the 3/2 is 8, and I would have a 0 like length to my strip at this point. So that tells me my visit to Planet Algebra was successful. Whew. Okay. All right, that's two ways to do it. Those are the two strips we would use. Now, obviously, we can put those together and use that area if we wanted, in which case these functions would end up somewhere in our limits of integration in the form of a double integral, and we would end up with one of these expressions when we integrate it. So that's more useful when we're doing polar, but for this one, there's no reason we can't just define strips. So we're starting with strip number 1 here. So let's go after x bar. Do 1 over a total, which we know is 19.2. And we're going to integrate from 0 to 8 inches. We're going to have x dA. Zero to 8 inches. And in this case, we're going to use the dA all in terms of x. So we have x. Now dA looks like we're going to use that dA. Hey, Cynthia. We're doing some 2D centroids. So I'll add another 3, so I'll have x to the 8/3. Zero to 8. Hui, do you want to calculate that for me? Is that 96? Okay, cool. So we're going to end up with if we put the 19.2 in for our total area, we end up with an x centroid of 96 divided by 19.2. It's about 100 divided by 20, so 5-ish. You want to get me a number for our x centroid? Well, stick at 5. Okay, great. Close enough. 3, 4, 5. So that's our x bar. Okay. So now we go after our y centroid. So 1 over the total area. Now we're going to integrate. I'm going to use that vertical strip. Or I'm going to integrate vertically. I'm going to use a horizontal strip. It sounds better. I'm going to use this one. dy. And my strip length is going to be the 8 inches minus the x value for a given y. So I had to, Cynthia, we had to get y in terms of x to do that. So I'm going to integrate from 0 to 4 inches, y dA and this time dA is going to look, dA is going to look like this, 8 minus y to the 3/2 dy. Go ahead and integrate or simplify a little bit. So that's 8y minus, y to the 2, so minus y to the 5 halves. So we'll do this one. That'll end up as 4y squared minus, add 2 7ths, I to the 7 halves. Integrating polynomials, we take away 1, 2 halves, give us 5 halves, and we're going to go between 0 and 4. Anybody want to calculate the integrand volume when we put our limits in? Really, it's just whatever it is at 4. Okay, so the integrand is 192/7. Okay, cool. So 27.43 is the value of the integrand. So 7.43 divided by our total area. What did that end up being? 1.43. Okay, that's actually good because we know it really should be down near the bottom somewhere because we've got more area at the bottom end. So that's our y. So our centroid is somewhere around where the red dot is. Is that making sense, everybody? Both of you? Okay, cool. So Cynthia, just as a recap, definition of centroid, in this case for an area. It's 1 over the total area. If we had some kind of linear thing, it would be 1 over the total length. If we had a volume, it'd be 1 over the total volume times the integral over that volume or length or area times a radius vector from the origin or whatever point we're picking, some reference point to any little bit of length or area of volume integrated with respect to length or area of volume, length or area or volume. So we're kind of averaging how much length or area or volume is on either side of that kind of center point. So centroid is, you can think of it as a balance point where how much of the length or area or volume of some geometric shape is on one side or the other, above or below, etc., in all of our orthogonal directions. And in this case, we can define a radius vector in terms of both of its components, plop it in, and now we can treat our x centroid and our y centroid separately because the integral of a sum is the sum of the integrals. And then the big trick is defining our differential area or differential length or differential volume in terms of something we can integrate that's going to change appropriately with that radius term. And the key is to make sure that the little bit of area, the differential area, is all, in this case, at the same y distance. Because in this case, for y centroid, we're defining, hey, how far is this differential element? Well, the whole differential element has to be at the same y. So there's the trick, is expressing our differential element such that it can all be at the same distance in any one of the orthogonal directions we're thinking about. So that literally becomes the math chase. And if we are defining our differential element with one side or length, that we can express one in terms of the other, that makes it a lot easier. There is a little trick to doing that. It's in my notes. I won't go over it in lecture today, but you can kind of bypass that. If you can't write a function in terms of each variable being the independent variable, you can take a strip, say we couldn't write y in terms of x like we did here. You can define a strip, write an expression for the centroid of that strip, and then average the centroids of all the strips up over x. So if you had to keep everything in terms of x, that's how you would do it. That's kind of a backdoor way of doing it. So you would be averaging the centroid of all the strips up over all the strips. Same concept, a little bit different way of getting at it, but it gives you the same answer. So that's what you do if you can't write one function in terms of the other. Okay, want to try another one? Yes, no, maybe.